Hi everybody, welcome to the last video in Trigonometry, section 9.4 and section 9.5. In these sections, we'll do operation on complex number, but it is in polar form. Right, so first, from previous section, we have a complex number z equal to a plus bi, where a is the real part, b is the imaginary part. If we put the real part in the first component and the imaginary part on the second component, then we have a point represent a complex number on two-dimensional space or in the plane. So pretty much we can also write z equal to x plus I times y. So x is the real part and y is the imaginary part, will be the vertical axis. So if we want to represent any number, this is the imaginary axis and this is the real axis. So in that case, if we want to represent, let's say a plus bi, we have a on the real axis and b on the imaginary axis. We will have a point, and this point is a plus bi. This point is a plus bi. The absolute values or the magnitudes or the modulus of the complex number is given by the distance from that point to the origins and defined to be denoted by similar notation as absolute values. So it says that absolute values of a complex number is equal to square root of a squared plus b squared, because this distance, after all, this distance is a and that distance is b, and we just have a right triangle, and that Pythagorean theorem. Now a squared plus b squared the same as z times conjugate of z. So this is very easy to verify. If we take z multiplied by z bar, z is a plus bi, z bar is the conjugate of a plus bi, which is a minus bi. Multiply them out, a square minus bi, abi plus abi minus b square I square. Middle term cancel out, I square is equal to -1. So that means a square minus b square times -1, so a square plus b square. And we take the square root on both sides. We have square root of a square plus b square, which is the magnitude or the absolute values of z. So we take the product of itself with the conjugate, take the square root, that is the same as the magnitude of that complex number. Right, that's easy because the x-axis is the real axis, the y-axis is the imaginary axis. Now we just plot the points. Plot this point. So 1 plus 3i, so we have 1 on the real part, 3 on the imaginary part. So this is 1 plus 3i. That point. Next, -2 plus 2i, -2 on the real axis, 2 on the imaginary axis, so -2 plus 2i. And then finally 3 minus 2i, 3 on the real axis, -2 on the imaginary axis. Yeah. So pretty much we have x component is the real for the real part, the y component for the imaginary part. And then this should not be a surprise. If we have the x and y, we can convert that to r and theta, so we can write a complex number in the polar form. So earlier we would say that x is equal to r cosine and y equal to r sine. Well, that's exactly what we're going to do. So if the complex number is z equal to a plus bi, or in this case, if we want to, we can say this is x and this is y. So x times I plus times I, y, and then we can factor out the r, and we have this number. So this is the complex number in polar form. It's going to be r cosine theta plus I sine theta, where z is the absolute values of number, or r is the absolute values of the complex number, and theta is called the argument of the complex number. Right. So simple enough, right? So we have x component for the real part, or r cosine, y component for the imaginary part, or r sine theta. Right. Let's look at some examples. Write the number square root of 3 plus I in polar form. So here we have, if we write that out, z equal to square root of 3 plus 1 times I. So we have the real part x, imaginary part is y. And here we can use just like what we have before, x equal r cosine theta, y equal to r sine theta, and then r squared is x squared plus y squared, r equal to square root of x squared plus y squared. Right, we have x and y here, substitute into that. So we have 3 plus 1, square of 4 is 2. So r is equal to 2. Now, the theta, it's just similar to polar coordinate. Tangent of theta is y over x, which is 1 over square root of 3. And so we can get theta as tangent inverse 1 over square root of 3. Right. Now, if we do the inverse, recommend that keep that in degree mode, so it's more familiar to see the angle in degree. Much better, right? 30 degrees. So if you can write 30 degrees, or we can write pi over 6. So we have theta, we have r, and the complex number in polar form is z equal to r cosine theta plus I sine theta. And z we do have is 2 cosine of, we can write 30 degrees, but I write pi over 6 plus I sine pi over 6. Yeah, so we can just write like that. That's easy enough, right? So write a polar, complex number in polar form. We do that a lot in this section. Right. Now, the other way around is easier. Write this in the rectangular form. So naturally, we just multiply 2 into it. So you have 2 cosine of pi over 3, and then plus I, and then 2 sine of pi over 3. Now 2 cosine pi over 3 is 1/2. And sine of pi over 3, I mean that is the 2, right? 2 I times 2 sine of pi over 3, sine of pi over 3 square root of 3 over 2. 2 and 2 cancel out, we have 1 plus the 2 cancel out as well. We have I square root of 3 or square root of 3 I. Yeah, so we write the numbers in rectangular form: x component, y component, the real part, the imaginary part. Right. Now, is there any advantage of writing a number in polar coordinate? And the answer is yes. If the number in the polar coordinate, so when we multiply them, we multiply the modulus, we multiply the absolute values, and then we add the angles. When we divide the modulus, and then we subtract the angles. So it is very easy to do if we have everything in polar form, that is. So let's look at the first example here. Let z1 be that, z2 is that, find z1 times z2. So z1 times z2 meaning that we'll multiply the conjugate. I mean not the conjugate, the modulo, sorry. 3 times 4. And then we will add the angles. 45 degrees plus 15 I sine of 45 degrees plus 15 degrees. Right. So we have 12 cosine of 60 degrees plus I sine of 60 degrees. Right. Didn't say that we have to give the answer in rectangular form, so we're just going to leave like that. However, this is easy. Of course, just multiply the modulo and add the arguments or add the angles. But why is that? Why do we have it? So I've just showed you the quick proof of it. So let's just say we have R1 cosine theta 1 plus I sine theta 1 times R2 cosine of theta 2 plus I sine theta 2. Right, now I attempt to multiply a number in general like this. First R1 times R2, that's easy. R1 times R2. And now we multiply. Cosine times cosine is cosine theta 1 cosine theta 2. Cosine times I, so that plus I cosine times sine and then plus I sine theta 2 sine theta 1 cosine theta 2 and then I square sine times sine. Now combine like terms. This I square is -1. So what we have is, if we group the part that have I and the part that do not have I, so we can say that this part does not have, these parts do not have I. So cosine theta 1 cosine theta 2, that is negative sine and sine. So those two parts do not have I. Put them together. And the other parts have I, where I will factor out the I. And we have cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2. Now, the last step is easy. Cosine minus sine. This is the sum of the cosine, right? And sine, cosine, sine. So this actually the sign of a sum. Yeah, so just basic, not basic, just the sum identities. We just have that. So multiply the modulos and add the arguments. If we divide, we will divide the modulo 3 divided by 4, and then we subtract the arguments. The top, which is 45 minus the 15 at the bottom. So that gives us 3 over 4 cosine of 30 degrees plus I sine of 30 degrees. So when the number is in complex form, it is easy. I mean, when complex number in polar form, it is easy to multiply and divide. Just going to do that. Next, if the number is in polar form, in rectangular, I mean, in radian measure, still multiply the modulo and then add the argument. Add the argument. That gives us 100 cosine pi over 3 and pi over 6. So that is 1/2 or 1.2 pi over 2. Then plus I sine. Right. Now when we divide, we just divide the modulo and then subtract the arguments. That gives us 4 cosine 1 over 3 minus 1 over 6. Yeah, what if we subtract? That would be 1 over 6. Cosine pi over 6. Right. So if the number is in the polar form, once again, it's easier to add. It is easier to multiply and divide. Right, just like that. Now, if we are given the numbers in rectangular form, and if we want to, we can convert them to polar form, and then in this case, find the quotient, meaning we divide them. Let's just say z1 divided by z2. Right, now let's convert this to polar form first. So z1 equal to 1 plus I square root of 3. So this one, x is equal to 1 and y is equal to 3. Right, so in that case we can find r square root of x squared plus y squared. We did quite a few of this. X squared plus y squared. Yeah, y square root of 3. So that would be 1 plus 3 square root of 4 is 2. Next we find the angle. Tangent of theta is y over x. Y over x, y is square root of 3, x is 1. So theta tangent inverse square root of 3, pretty much square root of 3. What's that? If this is in degrees more, yes. So tangent inverse square root of 3. we have 60 degrees. Yeah, I didn't say that we have to leave the answer in radians, so just give degrees, 60 degrees, right? So now we can write the Z1 in polar form. The radius or the modulo is 2 cosine of 60 degree plus I sine of 60 degree. Right. That is Z1. Now Z2. 2 minus 2I. By the way, remember, just like when we do the polar coordinate, when we do the tangent inverse, make sure it is in the right quadrant. 60 degrees in quadrant 1. And when we have x equal to 1, y equal to square root of 3. So this is in quadrant 1 as well. So this one is good. Don't need to do anything. Now this x is 2, y is negative 2. X is 2, y is negative 2. So it's here, which is in quadrant 4. Yeah, we just make sure that we have it. Right, we have x, we have y, so then we can find r square root of x squared plus y squared. Square root of x squared so square of 4 plus 4 square root of 8. Yeah, we can just leave 8 or square root of 4 and square root of 2 or 2 square root of 2. Square of 8 is square root of 4 times 2 square root of 4 times square root of 2 square root of 2. Yeah, that's what we have. And now the angle or the argument, tangent theta is y over x. Y is negative 2 and x is 2. So theta is equal to tangent inverse. That would give us negative 45 degrees, I assume. Negative 45 degrees. And is negative 45 degrees in quadrant 4? The answer is yes. So that's good. We don't need to do anything. The angle is good. Negative 45 degrees. Just keep that like that. So Z2, 2 square root of 2 cosine of negative 45 degrees plus I sine negative 45 degrees. Now, we divide them, right? Didn't say which divide by which, so just pick one. I would just say Z1 divided by Z2. Yeah, that's a quotient. Let's say Z1 divided by Z2. So we divide the modulo 2 divided by 2 square root of 2. And then we subtract the exponent, subtract the arguments. Cosine of 60 degrees minus a negative 45 degrees plus I sine 60 degrees minus negative 45 degrees. So that gives us 2 and 2 cancel out, 1 over square root of 2. Cosine of 60 and 45, that's 105 degrees. Plus I sine 105 degrees. Right. So it's not that bad. Yeah, of course, if we just multiply directly in rectangular form, that would be easier. Right? So we don't need to go to convert to polar form. But when we convert to the polar form, it is easy, even easier to divide them. Just divide the modulos and subtract the exponents. I keep saying that. And subtract the arguments. Sorry. So divide the modulo and then add or subtract the angles or the arguments. Right. Now, so that is where we multiply and divide. Now, in the next section, the next part of the section, we have the Morris Theorem. This theorem gives us a way we can find the powers. By the way, can we do that in the calculator? Oh, make sure it is in, I just want to keep integrated mode, even though we don't need to here. But most important, if we want to work with complex number, we'll select a plus bi, and now it's in complex mode. Now, can we do this? 1 plus I to the 4th power. Oh yes, -4. That works. So how do we do that? Of course, we can multiply that 4 times, right? But that seems like a lot of work. If we do this 4 times, yeah, that seems like a lot of work. I don't want to do it like that. But the Morris Theorem says, if it is in the complex form, all we do is raise the power to the n, and then multiply n to the argument. Right, so let's try that. I will convert 1 plus I convert the 1 plus I in the polar form. So 1 plus I, let's write out. Z is 1 plus 1I. Yeah. So we know X is 1, Y is 1. So we can find R is equal to square root of X squared plus Y squared. So which is 1 squared plus 1 square and square root of that. So square root of 2, right? Next, to find the argument, the angle. Tangent of theta is y over x. Both of them equal to 1. Which is 1. So if we want the angle to be tangent inverse of 1, the calculator will give us 45 degrees. Once again, if we don't need to, we can just leave this in degree mode. If the question is not specified, we can just leave this in degree mode, 45 degrees. Now, 45 degrees, 1 plus 1i, 1 plus 1i. So this is here in quadrant 1. And that is in quadrant 1. Yes, so that works. Right? So the angle in quadrant 1, so it's good. That means this number z can be represented in polar form as r cosine theta plus I sine theta, r square root of 2 cosine of 45 degrees plus I sine of 45 degrees. Multiply them out, but we don't need to. What we need is z to the 4. Now if the numbers in the polar form, it will be very easy to do the powers. That power will go to the argument. I'm sorry, that power will go to the modulo, to the 4th power. And then, yeah, I focus on this number 4. We go to the power of the modulo, and then we take that 4 multiplied by the arguments. Right, what is square root of 2 to the 4th power? Right, square root of 2 to the 4th power. Square root of 2 to the 4th power is equal to square root of 2 square, and then we square again, right? Power to another power, we multiply these powers, so that gives us 4. Square root of 2 square is 2, 2 square is 4, so that is 4. Cosine of 4 times 45, 180 degrees, plus I sine of 180 degrees. Now, multiply this all out. 4 times cosine of 180 degrees, plus I sine 180 degrees. Now, cosine of 180 degrees, this is -1. And sine of 180 degree is 0. So that's 0, and that is just -4. Right. So that is the advantage of the Morris theorem. We can essentially go to 100 powers or any power we want to. Just going to do that. I'm curious though. Let's say 97. Oh, it still works. Certainly works, yeah. But it's not to be anything nice and even. All right. Now let's do this. But I will change this problem to something more interesting. Let's go negative square root of 3 and plus I instead. You see why do I need to do that? Just make things more interesting, but how so? Right, so when we write like that, of course, we can write 1 times I. So x equal to negative square root of 3, y equal to 1. And we'll do the same thing, find r, find theta. R equal to square root of x squared plus y squared. Negative square root of 3 squared plus 1 squared. 3 plus 1 is 4, square root of 4 is 2. Simple enough. Right, now the angle. Tangent of theta equal to y over x. Y is 1, x negative square root of 3. So what is tangent inverse of 1 over negative square root of 3? Or just say negative 1 over square root of 3. That's better. Put the negative on the top. So is this in degree? Yes. So tangent inverse of negative 1 divided by square root of 3. That is negative 30 degrees. Now let's check to see if this is actually in the right quadrant. X equal to negative 3, negative square root of 3, and y is equal to 1. So we're talking about that point, which is in quadrant 2. Whereas here we have negative 30, which is quadrant 4. So this is in quadrant 4. So it's not in the right quadrant. So to get the exact answer, what we have to do is we need to add a pi to it. So I'm going to add 90 degrees to it. Sorry, 180 degrees, which is a pi. And so we end up with 150 degrees. Yeah. So sometimes we have to add 180 degrees. If the answer is not in the right quadrant, we can add 180 degrees or a pi to it. So make sure the answer is in the right quadrant. So at 150 degrees. Right now we have r, we have theta. That's good. Equal to r cosine theta 150 degrees plus I sine 150 degrees. Now when we raise to the 5th power, the power will go to the modulo, and then the angle will multiply by that number. So 2 to the 5th is 32. Cosine of 750 degrees. Right. So what's that equal to? Excuse me. Cosine of 750. That's square root 3 over 2 if you are familiar to it. So 750 subtract 360, get the coterminal angle, and subtract 360 again to get the coterminal angles, because 750 degrees is coterminal to 30 degrees. So this we can almost say, that it is just 30 degrees. Because from 750 degrees, if we subtract 720, which is 2 revolutions, so we get back to the same point, and that gives us 30 degrees, right? And then cosine 30 degrees, so we can say 32 square root of 3 over 2 plus I sine 30 degrees, just 1/2. And multiply this out, we have 32 divided by 2 is 16 square root of 3 plus 16i. Right. Now let's check negative square root of 3 plus I raised to the 5th power. We have that, and then 16i. And this number is 16 times square root of 3. Right? Yeah. So, yes, at this stage you said if we multiply this by itself 5 times, yeah, that seems like a lot of work. When we convert to polar, this is reasonably can be done. Right? So, again, the Morris Theorem, the power will go to the modulo, and that by complex number in polar form. The power, which is root, which is a little more complicated. So instead of we go to the root, let's say the n root complex number. So instead of raise the modulo to the n power, we take the root of the modulo, and instead of multiplying by n, instead of multiplying by it, we're going to divide. However, when we divide, we have to add 360 degree times k divided by n. The reason we do that because 360 degree is coterminal angles, right? Theta or theta plus 360 degrees times k. So we have to divide by a bunch of different angles, a bunch of different coterminal angles, divided by n. But as long as those results have to be between 0 and 360 degrees. So that's why k will go from 0 up to n minus 1. Because we don't want to go that over 360 degrees. We'll see. And so the n root of complex number is this. And how many of this? If we count from 0, let's say, if we have the cube root, we go from 0, 1, 2, and 3. Sorry, 0, 1, and 2. So for the cube root, there will be exactly 3 cube roots, 4 fourth root, and 5 fifth root. Depends on the index of radical. That will tell us how many of those do we have. Right, once again, take the root of the modulo and then divide the angles by that number. But that angle we divide by could be coterminal angles. So we're going to add 360 degrees times k, and k go from 0 to n minus 1. And we could use 2 pi if we have in radian. Right, so let's look at a couple of samples here. Cube root of 1 plus I. Now, I doubt the calculator can do this. 1 plus I. Cube root is the same as the power of 1 over 3. I doubt the calculator can do it. Oh, only give us one answer, which is not right. We're supposed to have 3 cube roots. Right, so certainly we have to do it by hand then. Right, first, need to convert this into polar form. Right, so convert one plus I into polar form. Look familiar. Did we do that before? Oh yes, we did. 1 plus I is square root of 2 cosine 45 degrees, I sine of 45 degrees. We did that, right? Yeah, 1 plus I. So let's not do that again. If we do that, z equal to square root of 2 cosine of 45 degrees plus I sine of 45 degrees. Right, now we just applied the root. So the root, by the way, let me just write out the n root of something is the same as a to the 1 over n power. So in this case, we can write this as, now we take the n, the third root. Z to the 1/3. Now if we have 1/3, first that 1/3 power will go to the modulo. Right, this part is understandable. And then because this is a third, we multiply that into the angle, which is also reasonable. However, we may have coterminal angle. So we not just simply divide by 3. We don't just simply do that. We have to have 45 degrees. Yes. Divide by 3. Yes. However, we may have coterminal angle. So I'm going to add k times 360, the coterminal angles. And it's 45 plus k times 360 degrees. And k, we know for sure k in particular will go from 0 to n minus 1. N is 3, n is the cube root, so we go to 0, 1, and 2. Now just do for each one at k equal to 0. By the way, let's just, what is square root of 2 to the 1/3? That's fine. Just square root of, for this example, we have square root of 2 is the same as 2 to the 1/2. Right. So the n root of a is a to the 1 over n. So square root of 2 is 2 to the 1/2. So we have 2 to the 1/2 to 1/3. power to another power, we multiply this exponent. We have 2, 1/2 times 1/3 is 1/6. So first, this is 2 to the power 1/6. Right. Now, when k equal to 0, just put 0 in for k. Z to the 1/3 equal to 2 to the 1/6. Cosine, since k is equal to 0, 45 divided by 3 is 15 degrees, plus I sine of 15 degrees. So this is one solution. The other solution, when k equal to 1, we have z to the 1/3 equal to 2 to the 1/6. Now k is equal to 1. 45 plus 360 divided by 3. So that 2, 1/6. Right, 45 plus 360 divided by 3. So that's 135 degrees. Plus I sine of, those should be the same. And there will be one more, k equal to 2. So the cube root, there will be 3 cube root, the square root, there will be 2 square root, and then 4 fourth root, and so on. And there's one nice properties about that. Right. Now k is equal to 2. 2 times 360 degrees, 720. So 2 and cosine 45 plus 720 divided by 3, 255 degrees. Right, so we have 3 answers. Here's 1, 2, and 3. If we want to check, we actually can check. For example, I can say this. First of all, 2 to the 1/6. And then I have cosine of 255. I just test one of them. Plus I, where's I? Times sine of 255 degrees. Right, I have that. If I raise that to the third, I have 1 plus I, right? So you can do the same thing for this one and the same thing for that one. All of them will give you 1 plus I. So there are 3 cube roots. Now, one more properties about this. All the magnitude will be the same. So, meaning the modulo will be the same. Meaning those points will be on the circle, right? So the nice thing about this is all of them will have the same modulo. They should have the same modulo, meaning that all of them will be on the circle. So I try to draw a circle here. Right, so I have a circle here. Because the modulo are the same, the distance to the origin will be the same. And now try to draw these angles. Right, 15 degrees. I'll just guess here, so about this much. So the distance is 2 to the 1/6, and the angle is 15 degrees. 135 degrees, we know for sure that is between split the second quadrant, right? So the radius also 2 and 1/6, but this is 135 degrees. And then 255. 255. We have 240, 225, and then so be about here. Now, we can check, but the root, on the root, we divide the circle in 3 equal segments. Of course, 15 to 130, so that 135, that's 120 degrees. 120 degrees and 120 degrees, and the modulo are the same. So this point will lie on the circle and divide the circle into 3 equal arcs. So that is the nice properties of the root of complex numbers. Will be on the same circle because they have the same modulo, and the angles will divide a revolution evenly. Right, so that's one of them. Next, find own the square root. By own, I mean 2, because square root is 2 to the 1/2 power, so there are 2 of them. Right, so first, negative 4i, I try to, of course, we'll convert that into polar form. But we don't have to do much. If we can draw it, we can answer the question without actually doing any math here. Negative 4i, where is that? So if this is the real axis, this is the imaginary axis, negative 4i, it will be here. Right, so it's easy to see that the distance from that point to the origin is going to be 4, so r is equal to 4. That's easy to determine, right? How about the angle? Well, it's also easy. We go 3/4 of a revolution, so which is you can say negative 90 degrees or 270 degrees. You can say 270 degrees, or if we want to 3 pi over 2. Let's just keep it in radian to keep things interesting. 3 pi over 2. Right, so I will write that in the polar form. R will be 4 cosine of 3 pi over 2 plus I sine 3 pi over 2. Right, now we want the square root, meaning that to the 1/2 power. Square root is equal to the 1/2 power. Right, so first that 1/2 power will certainly go to the modulo 4 to the 1/2 power, which is 2. Square root of 4 is 2. Now the angle. What do we do with the angles? We're going to divide by 2 because this is the root. But to guarantee we have all the coterminal angles, we're going to add k times 360 degrees. This case is a 2 pi. Three pi over 2 plus k times 2 pi divided by 2. That gives us just 2, right? Now, this is the square root, so we expect to have 2 of them. So one of them is k equal to 0, and the other one k equal to 1. We go from 0 up to n minus 1. n is equal to 2, so 0 and 1. Right, now when k equal to 0, have z to the 1/2, 4 to the 1/2 is 2 cosine. Now 3 over 2, which is 1.5, right? Just use the decimal 1.5 pi, k equal to 0, so just have that divided by 2. So 0.75 or 3/4, 3 over 4, so 3 pi over 4. And the second one should be the same. That's when k equal to 0. Now when k equal to 1. So when we have the square root, there will be 2 square root. The modulo will be the same. Now cosine. What we have is 1.5 pi times k is 1, so pretty much times plus 2, right? When k equal to 1, we have plus, so 1.5 pi plus 2 pi is 3.5 pi divided by 2 is 1.75, which is 7 over 4, and we stick a pi to it. Right, that's pretty much it. Now if this one, we actually can multiply this out. Cosine of 3 pi over 4, that is negative square root of 2 over 2. I sine of, I keep doing that. Sine of 3 pi over 4 square root of 2 over 2 is positive. Yeah, we can just look it up in the unit circle, that's fine. Multiply the 2 inside, we have negative square root of 2, and 2 and 2 cancel out, plus square root of 2, I square root of 2. And then this we have 2, cosine, that's going to be positive. That will be negative square root of 2 over 2. Multiply the 2 and 2, we have square root of 2 minus I square root of 2. So again, let's try to plot the result. Yeah, just have the steady hand and rotate the paper. Never rotate the hand, just the hand will be fixed. Rotate the paper. Both of them have the modulo of 2, so there will be in 2. 3 pi over 4, so this is like 135 degrees, so one answer is going to be this. Or if we want to, we can say that is negative square root of 2 plus square root of 2 times I. So that is the first one, right? The other one is radius is 2, the modulo is 2, and 7 pi over 4, so that is 315 degrees, right? Yeah. Times 360. Sorry, that I don't know why. 7 pi over 4, right? Pi over 4 times 180 divided by pi. So 180 divided by 4 is 45 times 7. That's 315. So we'll be here, which is square root of 2 minus I square root of 2. Yeah. So once again, these 2 points will split the circle evenly. One of them is at a degree of 3 pi over 4, which is 135 degrees. The other one is 315. Of course, they split the circle evenly, meaning that if you add 180, you get to that point, and add 180, you get back to that point, this point. Yeah. So whatever the answer is, they belong in the same circle because the modulo should be the same, and they will divide a revolution evenly. So there are two of them. So we split the circle in half. There are 3 cube roots. We split the circle in 3 equal parts. Right. Now with that, I stop this section here. As always, thank you for watching.